Become a sustaining member of the Commonwealth Club for just $10 a month.
Welcome to this evening's program of the Commonwealth Club of California. My name is Gerald Harris. I am the chair of the club's Technology and Member-Led Forum and will be your host for this evening. The Commonwealth Club is America's longest standing public forum. At this time in our history, we are proud to maintain our focus on informing the public and our members about key local, national, and world developments. The focus of the Technology and Society Member-Led Forum is to expose members and attendees to current and emerging developments in science and technology, and in the process generate thinking and ideas about the use and commercialization of technology in creating a better world for all. This is where real people can meet to discuss real issues and decide what actions might be taken. The place to be in the know. We want to welcome and encourage your participation in all of our programs. More information can be found at www.commonwealthclub.org. I want to not only welcome the people who are here in the audience, thank you for coming out, we're happy to see you, but also for those who are remotely viewing the program via our online channel. On behalf of the club, I would like to thank the folks at Wonderfest for their support of today's program in particular. At the end of some of the rows here, you'll find liberally distributed question cards. Please feel free to fill those out during Dr. Fechnoy's proposal. As a courtesy to the speaker, please silence your noise-making devices, phones, and things of that order. And now it's my pleasure to introduce our speaker, Dr. Andrew Fechnoy. He is Chair Emeritus of the Astronomy Department at Foothill College, former Executive Director of the Astronomical Society of the Pacific, astronomy and physics lecturer at the Fromm Institute at the University of San Francisco, and the OSHA Lifelong Learning Institute at San Francisco State University. He's also quite a musician in the sense that this month's Scientific American has great information on the beautiful topic he's about to talk about. Without any further ado, Dr. Fechnoy.
Thank you so much for that kind introduction, and welcome everyone. It's my pleasure tonight to talk to you about one of the most exciting things going on above our heads, which is the James Webb Space Telescope, which really is a giant eye on the invisible sky. And I want to show you some of the work it's already done, and I even have 2 slides that just came out this week, just to make sure that you get the latest results. The James Webb Space Telescope was launched on December 25th of last year after years of delay and problems. The most complex telescope we've ever launched into space, and it's operating, I'm happy to say, flawlessly 1 million miles from Earth with remote control across all that distance. But the story of the telescope really begins in the year 1800, when an amateur astronomer and musician by the name of William Herschel discovers that there are invisible rays coming from the sun. Herschel was a great experimenter, and he was playing around with a prism. You've played with a prism where light goes through the prism, it goes out in all the colors of the rainbow. He wanted to measure the temperature of each color of the rainbow. So he took a thermometer and carefully measured, and then he got to the red color, and he went beyond the red color, and the thermometer still kept going up in temperature. He said, whoa. And he started again, and he went beyond the red color, and the thermometer kept going up. Something invisible was heating up the thermometer beyond the red, below the red. So this eventually got known as infrared, just like infrastructure is stuff below the street. Infrared is a color below the red. And he discovered the first invisible rays coming from the sun. The infrared world, the infrared universe, turns out to be quite different from the universe you know with your eyes, and that's what I'm here to talk about tonight. Now, in fact, his discovery was only the beginning. It turns out that the universe shines with a great array of different invisible rays, and the light we see with our eyes is an incredibly small minority of the ways that the universe can shine. So we've had to develop telescopes and instruments for each of these other kinds of waves. You see them displayed at the top. Gamma rays, X-rays, which you know from your dentist, ultraviolet, infrared, microwave, radio, television, all of these, the cell phone frequencies that you use, wireless, all of these are invisible rays that inform us about what's going on in the universe. And so, because many of these rays are actually absorbed in the atmosphere, you see them in this diagram not getting down to the ground, we put telescopes above the atmosphere to tell us what's going on. And the infrared is certainly one of those where we need to go into space to get a good view. Now, we already had a good telescope in space, the Hubble, but it's now more than 30 years old, and its mirror size was limited by the size of the payload bay in the space shuttle which launched it. The bigger telescope, like the James Webb Space Telescope, you see here to scale with a person, the Hubble, and then the Webb, this telescope was launched folded, and it had to unfold like petals once it got to its destination. That was our biggest scare, that what if it didn't unfold? But it did. It did. It unfolded beautifully. And the bigger the mirror, the more energy, the more kind of light or infrared you can collect, and you can see how big this mirror is. The primary mirror consists of 18 hexagonal segments made of beryllium coated with gold. Now, they didn't just coat it with gold because it was a government project. Gold is actually a very good reflector of infrared. And so we use gold in a very tiny layer to reflect the kind of light we want to see. And the 18 segments have to be aligned perfectly to within 1,000th the width of a human hair. Think about that level of alignment. I mean, that's really pretty good, and it works. They did it. We know how to do this from mirrors we've already played with on Earth, but it's still a great achievement. The Webb telescope is 4 times further from the Earth than the Moon is, so it's roughly 1 million miles away from Earth. It's at a stable point where the poles of the Earth, the Moon, and the Sun are balanced in the right kind of way so that we can orbit the Sun and keep the Webb in our view. The height of the installation is that of a 3-story building. When it all unfolded and got organized, it's the size, the height of a 3-story building. Just the heat shield, which you see at the bottom below the mirrors, is the size of a tennis court. The whole thing weighs 7 tons. The sun shield keeps the sun's energy away from the heat-seeking telescope so well that it can stay at an operating temperature of minus 370 degrees Fahrenheit. Don't try to do that in your own refrigerator. In fact, the whole setup with the cooling and everything that had to happen, NASA reported had 344 single points of failure in the process of setting it up, and every one of those worked. So let's hear it for NASA. They don't always do things well, but this they did great. So here is the setup. Basically, energy, infrared energy, comes in, hits that gold mirror, bounces to the secondary mirror you see on the right, through the hole in the middle of the gold mirror to the scientific instruments which are behind it. And it's those scientific instruments that then analyze the light, make pictures for our eyes to see, and tell us what's going on in the infrared universe. The sunshade is always pointed at the sun and keeps the sun's heat from interfering with the delicate measurements we want to make. And I want to show you again a spread out view of the different kinds of light that nature sends us, with a focus on how tiny the visible light is. There you see the kind of colors and waves that the Hubble was sensitive to on the left, and then you see what the James Webb is sensitive to on the right. And you can see that the James Webb mirror receives and our instruments interpret a completely different kind of light. And so we see completely different pictures, and that's what I'm here to show you, the really sexy pictures from this instrument. But I wanted to set the scene for you. Now, why infrared? Infrared can show us things that we don't even suspect are there. Here's a really good illustration of a fire scene in visible light, where the smoke overwhelms your vision on the left, and then in the infrared, where you can see the prostrate form of someone who needs rescuing. And this is why firefighters use infrared scopes, so they can peer through the dust, through the smoke, and see what's going on. And in the same way, we peer through the smoke of the universe, through the dust of the universe, to see what's going on in ways that visible light can't show us. So before I show you the pictures you're all here to see, let's just talk for a minute about how the universe is organized. That way you'll be able to appreciate what's going on. I want to talk about the organization of the universe. And I'm going to do this at a basic level so we're all on the same wavelength, so to speak. So we begin with the fact that we live around a star which we call the sun. All the stars are suns. The only reason we see the sun so big is because we're close to it. And surrounding stars are planets. Here are the 8 approved planets of our solar system. And then stars, like the sun, don't appear by themselves. They're actually organized into giant systems we call galaxies. It's taken us a long time to figure this out, but despite what Texas says, there's no such thing as a lone star. Every star is organized into galaxies, and we are part of the Milky Way galaxy, and all the stars out there are in some sort of galaxy system. So that's one point. That's the organizational point. But I also want to remind you of how we know all this. We know all this because we get light, or infrared, we get waves of energy coming from the universe to tell us what's going on, and those waves travel at the speed of light. Infrared is also something that travels at the speed of light. And that speed is 186,000 miles per second, which in more familiar units is 670 million miles per hour. Okay, don't try to do this on your way home. This is, in fact, what we think is as fast as anything can go. It's the speed limit of the universe. That's a whole nother lecture why that's true. You have to just take my word for it. But everything we know about the universe tells us that that's the upper speed limit of how fast things can go. And although it's extremely fast, we live in a big universe. And therefore, it takes a while for information to get here. And that delay, that while, is a lot of what I want to talk about tonight. So we use a measure of distance called the light year, which is that distance that light travels in the course of a year. So we can all do the math together. 186,000 miles every second times 60 seconds in a minute, 60 minutes in every hour, 24 hours in a day, 365 and a quarter days per year. And you've all done this in your head. And the answer is 6 trillion miles. The distance that light travels in 1 year is 6 trillion or 6,000 billion miles. Now you might say that's a lot, but in fact the nearest star is more than one of these light years away. It's actually 4 of these light years away. The nearest star, which we call Alpha Centauri, is 4 light years away, so 25,000 billion miles. The key word for tonight is going to be a lot. Whatever I ask you, the answer is a lot. Okay, so 4 light years away for the nearest star, all the other stars are even further away. So it's going to be some delay before the information gets here. The most recent news you can get from Alpha Centauri is 4 years old, because light travels 1 light year each year, and therefore to cross 4 light years, it's going to take light 4 years. And we get 4-year-old news. Here's a famous star in the sky that some of you astronomy fans might recognize, Betelgeuse. See, shown with the red arrow as part of the constellation of Orion the Hunter. Betelgeuse is one of the brightest and easiest to see stars in the sky, but it's about 600 light years away, which means the light we see tonight left Betelgeuse 600 years ago, and the news we get is 600 years old. All right. That's the star picture. It gets even worse with galaxies. If you now look at how the stars are organized into these giant galaxies, and you look for a major galaxy, a galaxy you can bring home to mom with pride, if you look for a major galaxy, our closest major galaxy neighbor is 2.5 million light years away, where each light year is 6,000 billion miles. So that means the light we see tonight from that galaxy left there 2.5 million years ago, and it's 2.5 million year old news. Now, CNN fans say this is unacceptable. I want to know what's happening right now, but you can't. You can't see what's happening right now. There's a delay built into the universe because of the speed of light. And for astronomers, this is wonderful. Because what do you guys expect us astronomers to be able to do? You expect us to tell you the story of the development of the universe over billions of years. How could we possibly do that? The only way we can do it is by looking at things really far away, where the light has been on its way to us from billions of years ago, and can therefore tell us what was happening billions of years ago. Another way to put this is the further out we look, the longer ago we are seeing. And if you're new to astronomy, this is a mind-boggling concept, but it's really the heart of what I'm going to get to tonight. The further away from us we look, the longer the light took to get here, and the further into the past we're able to look. And we built the James Webb Space Telescope to look really, really, really far into the past. And I'll show you that in just a moment. All right. With that in mind, here then is the first Webb telescope image. It was released at the White House. It was a really awkward ceremony where no one quite knew what to say. And here's the image. All the things that don't have a spike are galaxies. And roughly speaking, the fainter the object, the further away it is. And so you're looking at really distant galaxies, tiny little dots, each of them consisting of billions of stars, but so far away they look like little dots. And I'll show you much more about this image, but that's the game here. With the James Webb Telescope, we can see really far and really back into the past. There are, we think, objects on this picture looking almost back to the beginning. And again, I'll show you that in more detail after we've gone in some order. Let's begin with the nearer objects. Let's begin with stars. And before I can tell you about stars, I need to tell you that stars, like people, have lives with stages in them. I like to divide the stages of a star's life into these categories because they parallel what people do. There's the prenatal stage, much in political debate these days, the birth of a star, adulthood, which lasts a long time, then a midlife crisis for every star, old age, where the star kind of falls apart, and then death, and then eventually you kind of put the star in the stellar graveyard. And each of these stages has been understood not for the sun, which is doing everything very slowly, but by looking at stars in different stages of their lives. And what the James Webb Telescope is especially good at is the first two stages. Star prenatal, star formation, and then the birth of stars. And we have great hopes for really learning a lot about how a star is born, as Hollywood says. And that's great because adult stars we see quite well with the Hubble. Here's a beautiful Hubble picture showing you stars of different colors. Most of these are adult stars doing their adult thing, and that's fine. The Hubble has done a good job with that. Where we need a lot more information is stars that are so faint and so shrouded with their birth material that we can't see them with the Hubble. And that's where the Webb specializes. Let me show you that. Star birth is often hidden. Here is the constellation of Orion on the left, as seen with our eyes and a good telescope. You can see the figure, which is the hunter's figure, the shoulders above, the legs below, and lots of stars. Bright stars make up the constellation figure. But you see mostly stars in visible light. Look at the same scene in infrared on the right. And what you see is the hidden raw material of stars, the stuff from which stars and planets and maybe even future Commonwealth Club members are formed. You see literally the dust, the dirt, and lots of gas, which transforms itself through gravity into stars and planets. The infrared shows you the visible light does not. All right, so let's take a look at one such region of star birth. This is called the Carina Nebula. It's seen here in visible light. You can see that as stars were born inside this cloud of raw material, those stars began to shine, and the light illuminates the raw material. You can see glowing clouds because stars have been born inside those clouds, and their shine makes the cloud shine. But I want to show you a specific region a little distance away from the main nebula. Here you see a young cluster of stars that formed relatively recently. They're only about 12 million years old, which for astronomers is really young. And there's a kind of cavity that you see here. I'll show you that better in just a second. Here's a slide to get you oriented. So there's the Carina Nebula, the whole nebula at the top left. The insert shows you the region I was just pointing to, which is a cloud of material giving birth to a cluster of young stars. Then the inset there shows you the wall of the cavity that these young stars have created. There at the bottom left, you see that region in the box. You can see winds from the star are pushing at that cavity. And then the rectangle in the bottom left transforms into the rectangle we see at the bottom right. And that's a Hubble picture with some exaggerated color of this little piece of this star birth region. And already with the Hubble, we see some beautiful things. We kind of see a wall of dust from the bottom, and then some gas glowing in blue at the top. But now I want to show you that same region with the Webb. And you can, I'm sorry, this is still the Hubble. I'm one slide behind, sorry. This is still the Hubble, just showing it to you bigger. It also gives you a sense of scale. That white bar shows you 5 light years across to give you a sense of how vast this cloud is. This is what the Hubble shows us. And here's the same region with the James Webb Space Telescope. And you can see that what looked like a region mostly of dust has actually got a lot of holes in it and many more stars. These stars shine more with infrared and not so much with light. And so we're looking into the cloud, seeing baby stars in the process of being born and seeing a lot more detail in the clouds of raw material. pictures like this are going to give us a much better understanding of the first stages in the life of a star. I think we're going to wait till the end for questions, but write it down, and I promise I'll get to all of them. So here is another nebula called the Tarantula Nebula. And what you're seeing here is a huge region 340 light years across. 340 light years across. And you can see that there's all this dust, the dark stuff. There's all the reddish stuff, which is gaseous material. And then in the middle, you see a cluster of stars. Do you see the cluster in the middle? That cluster was born very recently. Its energy is pushing out the center of the cloud, excavating, if you will, a cavity in the middle. And those cavities tell us that some pretty energetic adolescent stars are in the middle. Just like teenagers have way too much energy, these young stars have way too much energy and push out the material from which they formed. As they do that, they compress the material. They push it out and compress it. And from compression comes more gravity, comes more stars being born in the circle around. So we're seeing some beautiful images of star birth. And then this was a famous object for the Hubble Space Telescope. They nicknamed it the Pillars of Creation. And it looked pretty good with the Hubble, but here are two pictures of it with the Webb, which just make the Hubble pictures look pathetic in comparison. So on the left, you see a picture of the Pillars of Creation where you see young stars that give off infrared. So here you see that in this pillar of dust, there are many places where young stars have turned on. Those young stars are not yet hot enough to give off light, many of them, but they glow distinctly in the infrared colors that the Webb is sensitive to. Then they took another picture at a particular color and wavelength range where those stars are not visible, and the dust glows. And you can see that those same pillars are thick with dust, full of raw material on the right, even though they look a little bit transparent on the left. So depending on which kind of wave you're looking at with the Webb, you get information about different parts of the picture. Young stars on the left, raw material and particularly dust on the right. These pillars, by the way, are 4 to 5 light years tall. So you're looking at vast amounts of raw material and lots of star formation going on. All right, now I can't resist showing you one more picture in this domain, which came out last week. And I think it's really beautiful. And it's a little bit hard to understand, so bear with me. What you're looking at is a single young star still forming. And we can't see the star. Do you see in the middle, where in the very center there's what looks like two donuts with a dark line between them? That dark line is a torus or donut of dust which is hiding the baby star inside. But because it's in donut shape, every donut has a hole in the middle. And if you look up through the hole or down through the hole, things can get out. And so the energy of the baby star is getting out toward the top and toward the bottom through the donut hole. And the star isn't yet a real star. It's still forming. And now this is a terrible analogy, but it's burping. It's actually, as it's forming, it's not forming in a smooth way, but it's burping up material, like a young child would, burping up material. And if you look above in the orange region or below in the blue region, you see some curved arcs of material. Each one of these, if I'm not getting too personal here, is a single burp from this young star forming, where it let go of some of the material it was using to form above and below. So we're really seeing details we've never seen before of the process of the birth of a star. This is called the Dark Nebula L1527. It doesn't have a name, just the catalog number. But you saw it here first. This just came out last week. All right. Well, that's one thing I wanted to tell you about. Next, I want to focus on what is perhaps the most exciting discovery in astronomy in my lifetime, which is that in the last 30 years or so, we've discovered that there are planets orbiting other stars. We always hoped that there would be planets orbiting other stars. Star Trek was built on the idea that the Enterprise would visit a different planet every week, but we've never been able to prove it until recently. And now our observations just in the last couple of decades have shown us that there are exoplanets, exo meaning outside our solar system, exoplanets everywhere we look. The universe is crowded with planets. It's almost hard to find a star that doesn't have one. And so suddenly exoplanets are the rage in astronomy, and many of these exoplanets are in what we call the habitable zone, where water can be liquid, where temperatures are right, where perhaps life might be able to form. And so the study of exoplanets is another area where we have great hopes for the James Webb Space Telescope. Today we already know 5,000 established planets, and more are known all the time. And I want to focus in on one particular planet, which is given the terrible name of WASP-39b. WASP stands for Wide Angle Search for Planets. This is target 39, and the planet is called B. It's 750 light years away, and it's an interesting planet. It's a planet bigger than Jupiter, but weighs only 1/4 as much. So in order to be bigger in size than Jupiter, it must be heated, bloated, kind of all distended. And we now understand why that is, because it takes only 4 days to orbit its star. What? The closest planet in our own solar system is Mercury. It takes 88 days to orbit our star. The Earth takes 365 days to orbit our star. So 4 days to orbit is crazy, is disgusting, is impossible. But it is, we've now found this with many planets, that there are close planets much closer to their star. And WASP-39b is heated by being so close to its star. It takes only 4 days to go around. But because of that, there's a lot of energy coming from it, and we can begin to do studies of it. And here I just need to say something which I could spend hours talking about. Just like in the supermarket, a unique barcode identifies each item. So when you buy that mac and cheese, they know what to overcharge you for that container of mac and cheese. So in the same way, lines and colors in the spectrum of light uniquely identify elements for us. This is a science called spectroscopy. Every astronomy student spends many years learning about how to spread out the light or infrared of a star and to understand what the different lines are telling us, just like the different lines in the barcode are telling you different things. But from that, we can actually identify what elements, what compounds, what materials are in the star or in the atmosphere of a planet. And so what the James Webb Telescope is able to do is it's able to look at the light emitted by the star, seen in the bar above. Then it can tell that if the light goes through the atmosphere of the planet, as it is in this picture, you see how the star is on the right, top right. The planet is in front of the star. It has a thick atmosphere around it. The light of the star goes through the atmosphere of the planet. The atmosphere absorbs some colors, takes some colors out, and that can tell us what substances are in the atmosphere of the planet. By comparing the light of the star without the planet to the light of the star with the planet, we can tell something about what the planet's atmosphere is made of. That's really hard to do when planets are hundreds of light years away. But with the James Webb Telescope being so large and precise and out in space, we can do this. And I'm happy to report again that just this past week, a detailed report was published of the atmosphere of WASP-39b. And you can see labeled here the different substances they have discovered, some of them for the first time in the atmosphere of an alien planet. Look at the substances. First of all, there's water. That's not new. There's carbon dioxide. That's the first unique identification there. There's sulfur dioxide, carbon monoxide. We're talking about substances that we identify with organic chemistry here on Earth. Knowing what the atmospheres of alien planets are made of can tell us a lot about conditions on the surface and whether or not life might be possible there. So we'll be examining many planets with the Webb telescope this way, and I was hoping before I talked to the Commonwealth Club they'd have one success like this, and they came through. So let's hear it for the club. I'm sure they only did it because they knew that the club was waiting for this. All right, so that's another thing we're really looking forward to, identifying the chemical makeup of alien planet atmospheres. All right, let's move now to a much bigger realm. I want to take you now to the realm of the galaxies, where each object is not a star, but a huge collection of billions of stars, and show you again what the Webb can do. Here's a beautiful galaxy seen with visible light. It's given the catalog number M74. Here you see it with the Hubble. That bluish and yellow in the middle conglomeration is the light of billions of stars all shining together. And the Hubble can't make out individual stars, but it can make out the concentration of stars, which makes up the beautiful arms. Can you see the pinwheel shape? The spiral arms are made up of many, many stars in this galaxy. It's about 32 million light years away. That's what we see with our eyes. Now, here's what the Webb can show. You're not looking at stars, you're looking at raw material. This is the dust from which new planets, new stars will be made, a completely different image of the galaxy. Plus, I think it's just beautiful. I mean, we could just move it a few blocks, it would be in the Museum of Modern Art, right? I mean, it's really just a lovely image. The dust pattern, also spiral in structure, the raw material of another galaxy. Just absolutely a lovely a picture. All right. But one of the things that we've learned recently about galaxies is that they too are social animals. Just like stars gather into galaxies, galaxies gather into groups. This is a small group of 5 galaxies called Stephan's Quintet, after the discoverer. You see it here with the Hubble. Actually, only 4 of the galaxies are connected. The 4 at the top, I'm sorry, the 4 that are yellow, rather, on the right side. The blue one is an interloper and at a different distance. But this is what we see with our eyes. Now here's the same picture with the James Webb Space Telescope. You see much more connection between the galaxies. Material stretching much further out. Material which is actually being exchanged between the galaxies. You see again the raw material, but you see far more interaction and connectivity between and among these galaxies than we could see with visible light. And so these are the kind of images we're going to rely on to understand the social interaction of galaxies, the way galaxies not only interact with each other, but ultimately collide, which happens to a lot of galaxies, merge together into bigger galaxies. We think the galaxies we have today were built up from the collision, from the merger of smaller galaxies back in the past. And I'll get to that as we get toward the end of the lecture, but just a lovely image. Now, I want to show you Einstein looking happy, because now I want to come back to the first Hubble image that I showed you. I'm sorry, the first James Webb image that I have Hubble on the brain. The first James Webb image I showed you. This is the one released at the White House. And had Einstein been at the White House, he would have been smiling. Why? Because in 1916, 17, and from then on, Einstein proposed a new theory of gravity. A theory of time, space, and gravity, which we call the general theory of relativity, a complicated theory which has taken many years for us to fully understand and to prove correct, but which has now been validated in many different ways. And one of the things his theory said is if gravity is really strong, it can warp the fabric of space itself. Right. Say what? If gravity is really strong, strong gravity can twist, bend, warp space itself so it no longer behaves the way it normally does in the absence of gravity, but has kind of a bend, a warp to it. And if that's so, then if you have a galaxy with a lot of gravity, and light comes through that galaxy from further away to us, the gravity of that galaxy, Einstein said, might warp, might twist, might bend the light from behind it in weird ways. He proposed that it would be something like a funhouse mirror or lens. Have you been to a funhouse where you see a reflection of yourself, but you don't look like you look like some twisted, horrible looking thing, because the lens has warped, the mirror has warped your view, has warped your image. And that's what we're seeing here. We're seeing things that look like little arcs. Can you see that? I have an arrow next to them in a minute. And these arcs are warped light produced by the strong gravity in this cluster of stars. Here's an annotated view of that. And so you can see, for example, the arrows at the bottom point to those curved arcs. These arcs are the same galaxy from 9 billion years ago, 9 billion light years away, whose light is coming from behind this strong cluster of galaxies. And the gravity of the cluster in the foreground is taking the light from further away and warping it and bending it into these round arcs. And can you see the round arcs in every direction, kind of surrounding the middle of the picture? In the center is where the actual galaxy from behind is, but the light has been twisted by gravity into these arcs. This is called gravitational lensing. When Einstein proposed it, it was one of the hardest things for people to accept in terms of his theory. And now here you see direct proof that light is warped by the strong gravity of this cluster of galaxies. Not only that, but you can see arrows pointing to different little dots which are even further away galaxies. For example, at the top left, you see a light from a galaxy which we see as it was 13 billion years ago. Now, we think the Big Bang happened 13.8 billion years ago. So 13 billion years ago is pretty good. But it's not a record holder. We have even with the Hubble light from 13 billion years ago. There in the middle, you see an arrow pointing to a galaxy which is 11.3 billion light years away. So we're seeing light from 11.3 billion years ago. There at the bottom, you see one that says 13.1 billion years. That's, 1/10 of a billion better. Is that a record holder? No, not yet. Not yet. But they were very excited to get these, even in the first picture. Of course, they made this the first picture because they got it and examined it and made some measurements. They knew what they wanted to release. All right, but this gave us hope that we will be able to see things that send us light from really, really long ago. And now, just last week, we got the record. So this is two pictures from a cluster of galaxies. This cluster of galaxies is called Pandora's cluster. It's the result of the collision of 4 smaller clusters of galaxies. It's about 4 billion light years away. So most of the galaxies you see in the two pictures, the one on the left and the one on the right, both of those are different pictures of the same cluster. Both of those pictures show you mostly galaxies in this great cluster of galaxies, which is about 4 billion light years away. But shining faintly through that cluster, astronomers have found 2 even more distant galaxies. And those are shown on the central inset. And at the top, number 1 is seen as it was only 450 million years after the Big Bang. Is that the record? Nope. But below it is another little red dot, which is a forming galaxy, a galaxy in the process of forming, seen as it was only 350 million years after the Big Bang. And that's the record. They got the record. That's the most distant object we have so far identified. It is 350 million years after the Big Bang. Now, the Big Bang was 13.8 billion years ago. 350 million is 0.35 billion. So 0.35 billion out of 13.8 billion, 0.35 billion is nothing. This is still a baby galaxy, probably just forming, but already shining with the heat that we call infrared radiation. It is only 350 million years after the creation event, and already it has a unique, separate shape from all elsewhere. It's isolated into a blob, which is the scientific term for some unit, right? It's isolated into a blob already. You can see it in the middle of the inset number 2 in the middle. And that little blob in the middle is already, we think, disc-shaped. So it's flattened because it's rotating. And it's going to turn into probably something like our Milky Way galaxy, which is also flattened and rotating in the shape of a disc or a frisbee. The fact that something could form this early in the history of the universe is remarkable. The fact that we can look back to this early in the universe is mind-boggling. But that's what we've been able to do, even in this very first set of pictures from the James Webb Space Telescope. Ladies and gentlemen, I can only put it this way. We are now looking back to the dawn of time, to the first organization of matter in the universe. And the amazing thing is that this instrument that we humans built and put 1 million miles from Earth has the power to take us there. That's really something worth coming out on a cold night to the Commonwealth Club to hear about. Now, I've told you about a lot of astronomical wonders, a lot of big numbers and crazy concepts. It's a lot to take in. And you might have the reaction of the person in this cartoon. But I really like this cartoon a lot, so appropriate for our times. But what I want you to tell yourself as we draw to a close is this. We may be insignificant in size, certainly in the scheme of things that I've shown you, our little planet, around one little star in the outskirts of a rather average galaxy. By our size, we are really small and insignificant. But what's really significant is the power of our minds and the power of our tools. we have, despite all the trouble we have in getting along, we have been able to figure out the organization of the universe and to build tools to look back at the history of the universe in these remarkable ways. I hope you'll agree with the bumper sticker when thinking about the James Webb Space Telescope that these days astronomy really is looking up. Now, I'll end by just saying that this is a wonderful new era. We really look forward to all the things that are going to happen. And one way you can keep up, if I can say this, is I have a blog. Everybody's got a blog. I have a blog which is on my website, fracknoy.com. Somehow that URL was not in great demand, so I was able to get it. And so every few weeks, as new pictures come out, I not only post the pictures, but I post non-technical explanations, like I hope I've been able to do tonight, on that blog. So just go to fracknoy.com, go to the blog, subscribe, and then each time a new picture comes out, I'll try to explain it and make it available to those who subscribe. This really is just the beginning of the road, and I can't wait to see what happens. Thank you very much.
I have a few questions. We have about 10 minutes. I'm going to try to get to as many as I possibly can, but I think with that presentation being so fantastic, you're unbelievably well informed. Let me start off with, this looks like a pretty straightforward question, and it's from the audience here, which is, well, how long do we expect the telescope to keep working?
Yeah, great question. So because it's shaded from the sun, it's not being exposed to the heat that some other infrared telescopes were exposed to, and the coolant is not running out as fast. So they certainly have hopes of years and years of working. Now, the problem is it's in space, and space has dust in it. Some of the dust moving very fast. Space has little pieces of dirt in it, some of the dirt moving very fast. It has chunks of rock flying through it, some of the rock moving pretty fast. So isolated and unprotected in space, this telescope can get hit. It already has been, even in the stages where we were just rolling things out, it already got hit with a small particle. And they've got software to take care of that. They figured out how to isolate any parts that have been hit so it won't interfere with the picture. But there's only so many hits it can sustain. So let's hope that where it is not being used for target practice by the gods, that it's a relatively free zone, and that it won't get hit by anything big in the future. That's going to be a determining factor.
Great. And here's a question there's echoes of it in a lot of these questions here, which is, and I was watching this myself, these images, and because they're not photographs, right? Mm-hmm. So this whole coloring, the blue, the red and stuff, could you explain that in terms of how these images are made and colorized? Because that seems to be at the root of a lot of these questions here.
Excellent question and really important. So I'm glad someone asked about this. So yes, you can't see infrared with your eyes. So it has no color. Color is something we assign to visible light. And so what color are we going to use to color these pictures? Whatever we feel like. It's completely up to the astronomers, and we have incredible, but so they've made some rules for themselves. In general, with visible light, bluer colors are hotter and redder colors are cooler. Now, that's not what your art teacher told you. Your art teacher said it the other way around, but they're wrong. In science, I love art, my wife is an artist, but they're wrong. In science, reddish colors come from cooler things, bluer colors come from hotter things. So in the infrared, there's also cooler and hotter, all of them invisible to us. So they've made a kind of agreement that in general, the cooler things will look redder on the infrared photographs, and the hotter things will look bluer. But within that, they have so much choice because they can see so many more colors in the infrared, so many distinct, different kinds of waves than our eyes see with visible light. They have incredible incredible choice of what to do. And so each time a new picture is released, the team argues, okay, how are we going to color this? And then they have to say at the bottom of the scientific releases, there's a little chart that tells you what each color means. But the public doesn't get that. They just get the colors. And so the colors are not the same from picture to picture. They often are selected in the releases to make them look as beautiful to the public as possible. And so if you want to know what's going on, you have to go back to the website of the Webb telescope and look at the pictures and look at the translation code at the bottom left of the picture captions that tells you what each color corresponds to.
Okay, great. The next question is, so this dust, like where does it come from? Where does it on the side?
Great question. So where does the dust come from? Why is there dirt in space, basically? Because this dust is not that different from what you find under your bureau when you've been too busy reading astronomy books to clean up. So where does the dust come from? We think it comes from the death of stars. As stars die, they cool down, and so the hot gas, particularly as it's expelled from the dying star, the hot gas cools and coagulates and makes bigger and bigger particles. At first it's just atoms, and then it's molecules, and then as it gets cooler it coagulates and comes together into little pieces of material, and some of them have carbon and other things we associate with dirt and dust, and they make dust particles. So this dust comes from the end of stars, but it's also from these dusty clouds that the beginning of stars for the next generation takes place. So there's something romantic in that it's the dying material of the previous generation of stars that gives birth to the next generation and future generations to come.
Another very straightforward question. Who is this James Webb fellow?
This gets political. And every other telescope is named for a famous astronomer. Hubble was the great astronomer who discovered that all the galaxies exist. All the other space telescopes, we've had an agreement, name them after well-known astronomers we can all agree did great things. Along came one politically oriented NASA administrator and said, I think the next telescope should be named for a NASA administrator. What? For a bureaucrat? Said the scientists. But the bureaucrats thought it was a great idea. So James Webb was, to his credit, one of the great administrators of NASA. Under him, some of the moon program took shape. There's some discussion now that he didn't treat LGBT people quite the right way, but in his time, that was a very different world. But he was an administrator. He was a talented and in some ways influential administrator. But do we really want telescopes named after administrators? If you're an administrator, I apologize. But my answer is no. So that's the answer, the long answer to your short question.
Okay, we got three more here. So this is like this thing about how far things are away and the distance. How are we determining this so quickly?
Yes, and so this is a very fair question. And I like to say, how do we get distances in deep space? Well, we get a graduate student with a tape measure and we just send her out. No, obviously not. This could be a whole course, actually. How we get distances in space. The methods are indirect, they're complicated, they require knowing a lot of astronomy. And I have to confess, because this question makes me want to be honest, that these first distances that I've been sharing with you are not done in the usual way we get distances, which uses something called the Doppler shift in the motion of things. These distances are estimated from color, which is a rougher way of getting distances. So these are first distances and subject to change. Ultimately, we'll get much better at estimating distances. We'll use the more accurate methods, and some of what I said today might need to be revised. But that's always true in science. Science is a progress report. That's the best we know today. But measuring distances is very complicated. For galaxies, the main way we get distances is that we know now, thanks to Hubble, that the entire universe is in motion. that every galaxy moves away from every other galaxy because space itself is stretching like the skin of a balloon when you blow it up. And it's the stretching of space that carries galaxies away from each other. And so the further apart galaxies are, the more space there is between them, and the more they stretch, and therefore the faster they seem to move away from that galaxy that's observing them. So it's the speed with which galaxies move away that tells us in the most accurate way how far away from us they are. And that's what we'll ultimately be using to make these estimates.
Okay, I'm going to squeeze in two more. One, because you started this, so I may as well give this person a shot here. There's some debate about the speed of light. Has it always been the same? Has it differed? And you're saying these things are, this far away. So this question really has to do with, has the speed of light changed? Has it been different in the past and the future? It is gravitational. Can you say something about that?
Sure. And this was a proposal that got incredible attention from the creationist community. Because remember, the creationists want the universe to only be 6,000 years old, like Archbishop Usher said way back in the Middle Ages. And so if the speed of light changed, then you can't use the speed of light to tell where anything is. This was a theory that was proposed, a rather minor theory, and there have been tests to see if the speed of light is different, for example, within our solar system. Is it different as we go out and have radio messages come back from spacecraft we've sent to the edge of the solar system? And the answer is there's no indication at all that the speed of light is variable. Everything about Einstein's theories requires the speed of light to be constant, and so far there's been no violation of that principle.
Okay, last question.
All right.
Is the JWT going to tell us anything about dark matter, black holes, and all that?
Oh, yes, we hope so. So this is another 2-hour discussion, but let's see if I can give a very concise answer. Stars, when they die, often collapse to such a degree that Einstein's theory says the warping becomes complete. What happens if the warping becomes complete? Light, instead of going out in a straight line, comes right back in and twists back on itself. When you have an object so strong in gravity that light, instead of going out, comes back upon itself, you can't see that dead star, so we call that black. And if you throw something in, it'll never come back because gravity is so strong, so we call it a black hole. Black holes have now been actually found by how they affect space near them, by how they suck material in. Nobel Prizes have been given for this. And yes, we expect to learn a lot about giant black holes, what we call supermassive black holes, with the James Webb Space Telescope. Now, dark matter is something completely different. We've discovered that there is more gravity in the universe than there is light or other forms of radiation. So there must be matter out there that doesn't give off any of these forms of radiation that I talked about. Not light, not infrared, not X-rays, none of it. So if you can't see it because it doesn't give off any radiation, we call it dark. And just to make ourselves feel better, we've assigned a name to this invisible stuff. We call it dark matter. Dark matter is completely unknown. We only know it from its gravity. What it's made of is completely unknown, and therefore whether the James Webb Space Telescope will contribute to our knowledge of it is still an unknown. But you never know what's going to contribute our further understanding to things that are unknown today. So all I can say is what we say on the radio. We've got this great instrument. Stay tuned. Who knows what we'll learn.
Okay, all right.
Thank
Now,
you.
wait a minute, hold on. I've been informed we have time for 2 more questions.
Oh, 2 more questions. Okay.
yeah,
Why did I come
okay.
up with an
No, no,
ending?
no, no.
Okay, no worries.
So here's
No
another.
worries.
Okay, yeah. So this thing about the image that the James Webb is taking, is how long is an exposure? Is this just data coming in and these images? How, you got these 18 mirrors. How does this work?
That's great. And the best I can say is that each picture is different. So there, you can collect light for a short time and see only the brightest parts of the picture, or you can collect light for a longer time and see fainter things. So depending on what they're looking at, they collect infrared radiation, not light. They collect infrared for longer and longer times. The Hubble was known for taking exposures, for collecting light for many orbits, going back to the same object, orbit after orbit, and collecting weeks and months of radiation because it's such a small telescope. Because this is so much bigger, it can do in a couple of days what it took the Hubble months and weeks to do. So we can collect light more efficiently. There may still be things so faint in infrared that we will collect light for a much longer time and add the light together orbit after orbit. But for the time being, we have this wonderful advantage that with a bigger mirror, you can collect more light, more infrared to begin with. And so we can see fainter things more quickly.
Okay, here's your last question.
All right.
Because you kind of indicated this in your talk, which is that, well, wait a minute, if this galaxy that was found way out there that's only 300 million years after the Big Bang, well, how long does it take to form a galaxy? Like, wait a minute, doesn't that seem like a short period of time for all this to happen? So it seemed like you were a little puzzled yourself about this.
Extremely perceptive question. And absolutely
This is Commonwealth Club, you know, come on.
Yeah, that's right. That's
I have
right.
this
So this is going to be one of the problems PhD students are going to work on for the next few decades. How the heck did the galaxies get organized so quickly after the Big Bang? How did the Big Bang, which threw out all the matter and energy that exists in the cosmos and was full of chaos, how did it organize itself by gravity so quickly? Now you might say 380 million years, that's a lot compared to my lifetime. Doesn't seem, but for astronomical things, that's a very short time, as your question implies. How did the universe get organized so quickly? Many of our theories said that it would take longer than that. So as the question implies, we're going to need to really think a little bit more about how the universe first got structure, how it got organized, how matter came together. Is there something else like dark matter required to bring it together this quickly? There's going to be a lot of exciting work to do as a result of these discoveries of early galaxies at the dawn of time.
And we look forward to inviting you back to explain it all to us. Please join me in fantastic. Thank you so much. This concludes the program of the Commonwealth Club of California. Thank you all for your attendance.